creating an electromagnetic wave is only the beginning. Once a wave leaves an antenna, how does it travel through space? Why can some signals reach thousands of kilometers while others fade after only a short distance? To answer these questions, we need to understand wave propagation. In the previous lesson, we learned how antennas generate electromagnetic waves by creating changing electric and magnetic fields. Once formed, these waves carry energy and information away from the transmitter. However, generating a wave does not guarantee successful communication. A signal may travel through free space, pass through buildings, reflect from obstacles, scatter from objects, or become weakened over distance. As a result, the signal received at the destination can be very different from the signal originally transmitted. The challenge for RF engineers is understanding how electromagnetic waves behave after leaving the antenna. Predicting this behavior is essential for designing communication systems, planning wireless networks, and ensuring reliable signal coverage. This study is known as wave propagation. Wave propagation refers to the movement of electromagnetic waves through a medium or through free space. It describes how electromagnetic energy travels from a source to a destination and how the surrounding environment affects that journey. As electromagnetic waves propagate, they transport energy through space at a finite speed. In free space, this speed is the speed of light. During propagation, the wave may interact with objects, materials, or atmospheric conditions that modify its behavior. Propagation is not simply about movement. It also involves attenuation, reflection, refraction, diffraction, scattering, and absorption. Understanding these effects allows engineers to predict how signals will behave in real-world environments. Intuitively, wave propagation can be compared to ripples spreading across a pond after a stone is dropped into the water. The disturbance moves outward from the source, carrying energy away from the point where it originated. Physically, consider a cellular base station transmitting a radio signal. The electromagnetic wave expands outward through space. Some energy travels directly toward users, while other portions may reflect from buildings, vehicles, or terrain. Different propagation paths can ultimately reach the same receiver. Mathematically, as a wave moves away from the source, its energy spreads over a larger area. Because the same amount of energy is distributed across increasing space, the received signal becomes weaker with distance. This fundamental effect is one of the primary limitations in wireless communication systems. Wave propagation is one of the most important topics in RF engineering because communication performance depends heavily on how signals travel through the environment. Engineers must understand propagation behavior when designing cellular networks, satellite systems, radar installations, and wireless communication links. In urban environments, signals may experience multiple reflections from buildings and structures. In rural environments, terrain and atmospheric conditions often become dominant factors. Satellite systems must account for propagation through the atmosphere, while indoor Wi-Fi networks must deal with walls, furniture, and other obstacles. At the system level, propagation determines communication range, signal strength, coverage area, link reliability, and network capacity. Accurate propagation models are therefore essential for successful RF system design. Wave propagation explains why signal strength changes with distance and why communication performance varies from one environment to another. Even the most powerful transmitter cannot overcome the fundamental laws governing electromagnetic wave behavior. A common misconception is that electromagnetic waves always travel at the same speed under all conditions. While waves travel at the speed of light in a vacuum, their speed changes when they enter different materials. The properties of the medium influence how quickly electromagnetic energy propagates. This observation leads directly to the next topic. In the next lesson, we will explore speed of light in media and discover why electromagnetic waves travel at different speeds in different materials and how this affects RF systems. In this lesson, we learned that wave propagation describes how electromagnetic waves travel through space and interact with the surrounding environment. We also saw how distance, obstacles, reflections, and material properties influence signal strength and communication performance. In the next lesson, we will explore speed of light in media and discover why electromagnetic waves do not always travel at the same speed in every environment. If you found this useful, like the video, subscribe, and follow for the next lesson.